All right, so that's what you want to practice. Get your models to help you with that. I'm going to take you through some other structural peculiarities you'll need to be comfortable with. I keep saying aldohexoses. There's only one important, at least, that you need to be comfortable recognizing is the one that's a ketose is fructose. You've heard of that, right? The fruit sugar, fructose. So notice how different it looks. It does not have a CHO at the top, no aldehyde at the top. It's the second carbon from the top. The CH2OH has two of those CH2OHs. The one that's attached to the carbonyl is the one that gets the head priority. Okay, so we keep that as the head, the ketone. And the tail is our usual CH2OH. All right, so that's how you orient a ketose if you need to work out the Fisher projection for that. Okay, this word, hemiacetal, comes up again. It's important biologically speaking. We alluded to that a little bit in our hemiacetal unit. But I'm going to remove, this is actually cut and pasted from the hemiacetal unit. So what this represents is just removing all those little stereocenters because they're not part of this reaction. But what I want you to recognize is that we can actually react the terminal alcohol with the aldehyde on the other side in a nucleophilic attack, right? So this could do attack open, but we'd have to protonate first. That's where the H plus comes in. So we know how to make this. We know the mechanism. So I'm not going to overly belabor that, but I will talk you through it because we've had a test on that. Attack open after it's been protonated. So protonate, activate, attack open. We have a ring. 1, 2, 3, 4, 5, 6. Okay. I keep saying I'm not going to draw it, but I can't resist. I'm going to draw it. So let's do it. I think it just helps. So protonate. Now it's activated. Attack. Open. Okay, draw those numbers again. 1, I'm starting with oxygen because it attacked. 2, 3, 4, 5. It attacked what? This carbonyl. So that's 6 members of my ring. The oxygen is one of those members. So you draw a cyclohexane with an oxygen incorporated in there. Let's go back to our numbers. 1, 2, 3, 4, 5, 6. 6 was the carbon that got attacked, open to an alcohol. Now a stereocenter. O still has its H on there, so we'll neutralize. And get home to the, let me shorten that arrow a little bit, kind of a little crazy with that. So we have these pieces in our carbohydrates. We have a terminal OH, we have an aldehyde. They can be in equilibrium with the closed ring form. What is the functional group called? Hemiacetal. Okay. So what does that look like when you add in all of those groups? More complicated because you have to work out where the stereocenters go. So think about that one. Let's close glucose into a ring. And this is one you'll want to recognize the ring form of, as well as the open chain form. So notice it's not a Fisher. This is drawn in its bond line format here. Let's number the carbons. We are going to attack with one of the oxygens. And we know that we need to end up with a 6-membered ring. So we're going to attack that carbonyl. But there's so many oxygens now. Which one's going to do it? So 6, 5, 4, 3, 2. Look, it's not that one that's way out on the end. That would make a 7-membered ring. We want a 6, so it's actually this one. That's the one that attacks. So I found that by counting backwards. And this can be rearranged And look, I have it all ready to close the ring here. So I'm going to renumber it. 6, 5, 4, 3, 2, 1. So stereocenters are intact. This is sort of like a semi-chair getting ready to close. It's going to look like a chair when it's done. So what we're going to do is I'm going to do a shorthand version of the mechanism. It gets activated, and we attack and open. In fact, I can make that even shorter, just because that's not the nature of this chapter. We could do that. Okay, so we're closing right there. What does that going to look like? Well, we have, I'm going to give myself lots of space for it. Look at how we have a chair with an oxygen as one of the carbons, in place of one of the carbons. And remember, in a chair conformation,
remain seated, please. Permanecer sentados, por favor. Remain seated, please. Permanecer sentados, por favor.
Look at all this 3D stuff coming back. Chair conformation, the up carbon is, so it's a zigzag hexagon, right? So we have down carbon, up carbon, down carbon, up carbon, down carbon, up carbon. They alternate. So if you have an up carbon in front, there's a down carbon directly behind it. And it's 3 sets of parallel lines. Parallel there, right? Every opposite bond is parallel. Parallel there, and then these are parallel. So if you've drawn your chair correctly, you have those 3 sets of parallel lines. Great review for the final, right? So let's draw that chair. Now let's draw in all our groups. This is equatorial. If you aren't sure, you could draw the H's in to see how they would look. Down carbon has a down group. Up carbon has an up group that's axial. So the ups and downs have ups and down axial. So down carbon has a down axial. Up carbon has an up axial. And I won't draw in the rest of the groups yet because we'll kind of do that little refresher. Down carbon, down axial. Equatorial, parallel to the opposing bond. Up carbon, up axial. Equatorial, parallel to the opposite side of the ring. Down carbon, down axial. Up carbon, parallel to the opposite side of the ring. What do I mean by opposite? This is opposite that. This is opposite this. This is opposite that. So those are all parallel. Fill them in. So that's equatorial. H was above. That's axial on this particular carbon. Axial does not mean above or below. It's because remember, it's half and half, above and below. So we have to really pay attention to what's above and what's below when we go through this. Carbon 5 has equatorial and axial H. So equatorial OH, axial H. Carbon 2 has that CH2OH. Carbon 6 opened up. This is the one that could be different. Because we attacked, we don't know if we have this one or, let's draw the chair again. Don't worry, it's exactly the same except for that one carbon. So I'm going to put a little star here. Okay, so they're all stereocenters, but I'm asterisking that one for a reason. So we're going to have the opposite scenario there, just to make sure we do that right. Then copy the rest, this as is. I'm not going to draw the H's in this time. It's not necessary, unless you're just doing it for clarity. So it's not a chair flip. These are the same chairs. It's just that when you attack something that's sp2 hybridized trigonal planar, you form a stereocenter potentially because you make a tetrahedral carbon. And if that tetrahedral carbon has 4 different groups attached, then you do have a stereocenter. So because we formed a stereocenter, we have to acknowledge that it could have formed either way, with the OH going up or the OH going down below. So we get both. Which one's major? What would an organic, well, if you took this to the 211 class and you said, which chair is more stable? What would they say, hopefully? Organic 1 class would say, they would all vote for equatorial OH versus the axial. They would expect that. Okay, so which is major? Your prediction, and this is OChem 1, which means you know it's not right.
Oh, snap.
Otherwise I wouldn't harp on this, is equatorial OH. Turns out this is major. Why was equatorial OH's major? It always gave it more space. We did the double Newmans to prove that, built models to prove that. So I'm not going to hash that all out. But if you're not convinced, build a model, build one with equatorial H and axial H, and see which one can bump into it more and have more steric interactions. Okay, so I'm going to write out the answer and we'll work through it. Now, I say axial and then I say equatorial, and I say, wait a minute, there's lots of stereocenters. Equatorial what? Which one's axial? There's a name for this carbon that has the asterisk, the one that got attacked, that can produce the two new stereocenters. That's called the anomeric carbon. So I'm going to write that here, anomeric C. Sometimes also called, because it can have those two different stereocenters, especially because this is an equilibrium, it's opening back to the straight chain form, closing again with a different configuration possibly, then opening, then closing with the other configuration, right? That means it's not fixed at that stereocenter. So that's called, for that reason, also called a mutarotatory carbon when it can do that. So let's put that here. Mutarotatory. Okay, so a couple other things to point out. First, we want to understand why this is kind of a surprise, right? We're confused. We should be confused by that because we spent so much time in 211 making sure we understood why equatorial groups that were bigger were favored, and why would we put a small h equatorial and let the bigger OH with lots of electronic repulsion axial. That's the first question. So you can draw these by hand if you want, or you can you know, kind of use this to kind of, I feel like my drawing gets a little limited once I start drawing a chair with an orbitals on it. But there's a reason for this, that the equatorial OH is not as favored as the axial. So we'll soon learn that not only will we form hemiacetals, but also this is an acetal because of OR instead of OH, or OH. Okay, but notice that if we take this, and let me just put this, okay, so let's take a minute to take a look at this. Here's our oxygen that's in the ring. Here's our anomeric carbon. I don't want to cover my words, put it right there. Here's our anomeric carbon. Here's our axial OH or OR. When it is lined up axial, it allows the orbitals to overlap. So they are parallel. So this orbital that's on this carbon that's sp3 hybridized, it's empty p orbital. It can allow the overlap, actually it's an empty sp3 hybrid orbital, because this is also sp3 hybridized. So this can allow the overlap of the lone pair, which is electron rich, into the neighboring hybrid orbital, which is less electron rich. Remember, so this is more electron rich in terms of oxygen's electron density. So it's an electron, you know, sort of diffusion sort of argument. It stabilizes the electron density by delocalizing it. So it's a form of delocalization. You're not literally drawing resonance, but it's kind of like hyperconjugation. So you can rotate, if you can rotate a bond to alleviate the positive charge by donating an electron in there, it's the opposite. You can rotate this bond such that its parallel orbital will allow it to accept electrons. So I would say it's the opposite of hyperconjugation, but the same idea. It's just the reason it's the opposite is the direction of donating or accepting. So the carbon's accepting electron density. Or in hyperconjugation, it's donating electron density. So in other words, it likes to approach a more even distribution of electron density, and this allows it to do that. So delocalize electrons if orbitals are parallel. They must be parallel. This path doesn't work if they're not parallel. Second reason, you can kind of see if you draw in the dipoles. So I have the chair here drawn. So feel free to draw it in, but it was a little bit more nicely drawn here. Here we have our group, the OR or OH equatorial versus OR, OH axial. Let me move it over because I know that I'm here. So, what does that mean? Dipole minimization. So look at how when you draw the dipole when it's equatorial, notice they're going the same direction. With vector math, you're adding them. Higher magnitude dipole. That's not a stabilizer. That's a destabilizing. Increasing the magnitude of dipole destabilizes the molecule, makes it more reactive. Decreasing the magnitude of the dipole would mean do not let them line up in parallel. Parallel is where you get the biggest additive effect. Okay, so this minimizes it. So notice how when we draw the dipoles when it's axial, we minimize that dipole. So you don't have to go calculating them, but it's visually kind of apparent there. So there's two reasons. We call that the anomeric effect. So this is it explained here. Anomeric effect. But I'm also going to reference it here because that poor confused guy needs an answer. Anomeric effect. Right? Okay, so something else to know about this ring forming exercise. So not only do we get those two possible anomers, okay, I'm gonna write that there. They differ specifically at the mutarotatory carbon when they close the ring. Not only do we get those two possible anomers, we know that this is D-glucose. And we also know it's still D-glucose in the ring form. So it's still D-glucose. However, in the ring form, it looks different than the straight chain form. So what do we call the ring form to set it apart from the straight chain form? So the one that has the ring, we include the name pyran because it's a six-membered ring with an oxygen, and put the os ending to indicate it's a sugar. So remember, pyran is this. That's our heterocycle with oxygen as part of the six-membered ring. If it's part of a carbohydrate, then it's a pyranose. Sometimes it's pronounced pyranose. So pyranose is when it's in the ring. So this is a glucose pyranose, or how are we going to say that? Actually, we're going to name it more fully because we have two anomers to consider. They need a name because there's two different ones. So we need a name for each of them. And then we have to make sure we acknowledge that it's a ring. So it's going to be, its correct name is going to be glucopyranose. They were both D because we started off with the D sugar as indicated before. And then what is alpha and beta? That's going to tell us which anomer we have. Okay, so let's go find which one's alpha and beta, because we need to get the full name down. Okay, so the anomer has to be involved in this, and our reference point. So we could say that here we have the OH up, here we have the OH down. When the OH is up or down, the other groups may be down or up as well. So we're going to pick a point of reference, and it's going to be that CH2OH. So because I could do a chair flip and get confused about all the different orientations possible, but this will keep it consistent. Circle let's see, I'm going to do red. Circle the CH2OH. It's always on the other side of the oxygen in the ring. So notice that this ring, the Pyranose that formed, on one side it has our anomeric carbon. On the other side it has the carbon with the CH2OH. Find that, and then find the anomeric carbon. Circle that OH on the anomeric carbon. When they are on the same side, cis, CH2OH, and anomeric OH. We will call that the beta isomer. Okay, so this is beta. If they are not on the same side, then they are going to be by default the other one, the alpha isomer. So they'll be trans to each other. Let's prove that for the other one as well. Here's my anomeric carbon. There's my anomeric carbon's OH. There's my oxygen in the ring. On the other side, I have my CH2OH. This is up. This is down. Trans. Therefore, alpha. Okay, so beta, that answers our question. Beta D-glucopyranose is here. Alpha D-glucopyranose is there. Wow, we had a lot of work there. That's worth studying some more. Maybe even redo this one without me on another sheet of paper, because we're going to switch gears and do 5-membered rings next.
Five, four, three, two, one. 5, 4, 3, 2